Hi everyone, welcome to the start of a new series. Now, we are continuing on from our previous series of quadratics and quadratic equations and applying this to sketching the curve that corresponds to these, which is the parabola. Now, we've talked about parabolas a lot in the past. We've looked at sketching those. We've looked at the types of transformations that we can apply to parabolas, and pretty much what we're doing in this video is we are applying the new concepts we've learned. So in the previous series from the year 10 content, we talked about completing the square, this process of factorization for our parabolas, and we're going to be applying this now to sketching parabolas in a different way. Now, this is, like I said, a lot of revision from the previous year's content. So I'm going to go through some of these concepts in this video, the ones that are relevant, but if you would like a refresher, please look back at those old videos because the content here is going to assume that you've got your head around the things we did in parabolas from the year 9 series. Okay, so completing the square, what this essentially allows us to do is express a quadratic in the forms of y equals our general formula, ax squared plus bx plus c. We're going to look how this happens later, but this allows us to get this guy here into the form of y equals a x minus just some constant, we'll call that h, plus k. Now, if you remember last year's content, then, the last topic on completing the square, you may recognize this type of form, but this particular thing here, don't worry so much about what these letters all mean. They're just numbers that we're going to end up substituting in, but these tell us some very interesting things about the parabola we end up sketching. If you remember this guy here in front, that is our vertical dilation. So we looked at last year how this can, if this is a positive number and as the number gets bigger, my parabola gets stretched out, it gets steeper, or it can get wider as we go into the fractions. And the sign of this, so whether this is positive a or negative a, that depends on the reflection. So whether this will be a concave up parabola or a concave down parabola. Now this guy here, or this whole thing I should say, this was our horizontal translation. So this would tell us whether this was shifted left or right. And it gets shifted by the amount of the value that is made up by this h here. And finally, my k, that tells me if my parabola was shifted up or down. So this is what we call our vertical translation. Okay, so let's just do one example with an already factorized quadratic expression or equation, and we're going to look at some of these main key points here and try to draw this and just identify what these features in this particular form can tell us about what the parabola looks like. So, for example 1, I'm going to give you this thing here, y equals minus 4 x minus 1 all squared plus 16. Okay, so let's look at what each of these mean. Now, my -4, we have a vertical dilation. So this is going to get a little bit steeper, but this particular negative tells me this is a reflection. This tells me whether the parabola is concave up or concave down. Now, since this number is negative, our parabola, from what we remember in last year's content, is going to be concave down. So, since it's concave down, it's going to have some kind of maximum turning point. Okay, and we have one piece of information from here, so that's our reflection. This tells us it has a maximum turning point somewhere. Now, if we remember over here, let's actually just highlight this and drag it down. This part here told us where the vertex was getting shifted. So our point here is going to move left or right depending on whatever this value is. So this is x minus 1. So remember, with the horizontal translations, we go in the opposite direction. So since this is x minus 1, we are going to go shift to the right 1 unit. So 1 unit to the right in the x direction. So if this was, for example, drawn on an xy plane, you would see that the pointy bit, the x coordinate, is going to be 1. It's going to shift across. And finally, we have this thing here. We have positive 16. So this means we are shifting. We are going to shift up 16 units. Now, I'll ask you guys a question. What is going to tell us about the turning point? Which are the key bits here? Well, all of these are actually pretty important, because the reflection tells us whether this is a maximum turning point, because we need to determine that as well. My horizontal translation, this x minus 1, that tells us where what the x coordinate of my vertex is going to be, and my 16 tells me the y coordinate. So my vertex here, or my turning point, sorry, the coordinates of my turning point are going to be 1 and 16. Now, we will obviously look at how this is going to look once we end up drawing it. But for part B, we want to find the y-intercept. So remember, from the previous series on parabolas, we looked at how we can find these different x and y intercepts using what we learnt from linear relationships. So the y-intercept happens when x equals to 0. So I can substitute that into my equation up here. So my y is going to equal minus 4 times 0 minus 1, all squared, plus 16. Okay, so this is going to give me minus 4 plus 16, and then that's going to give me 12. So this is my y-intercept here. And finally, I want to find my x-intercept. And I get this when y equals to 0. So subbing that in, I get 0 equals to minus 4 outside of x minus 1 all squared plus 16. And I'm going to want to solve this equation. little by little. So what I'm going to do first is I'm going to subtract 16 from both sides, because I want to isolate x, so I work from the furthest things away from x back closer and closer to it so I can isolate it. Okay, so now I can get rid of this negative 4 by dividing both sides by 4. By dividing both sides by negative 4, I should say. And I end up with 4 here equals to x minus 1 all squared. And then now I can just solve this by taking the square root of both sides. So the square root of 4 gives me plus or minus 2, because remember I can have two solutions, and that equals x minus 1. So that means that I have two possible solutions here. I have that x minus 1 could equal positive 2, and x minus 1 could equal negative 2. And now I just want to solve this. So here, we've done this plenty of times before. Some of you can probably figure this out just by looking at it. I want to add the 1 to both sides here, and I want to add the 1 to both sides here to give me negative 1. So these are my x-intercepts here. And we remember that no matter what method we use for solving these equations, now we could have also done this in a slightly different way as well. If you remember from when we looked at the two methods of finding the x solutions when we were completing the square, I've done method 1 from here. You can consult that previous video and look at how we can do it for method 2. I'm just a bit conscious of time, so we have to get through these. Okay, so now we have all of the key bits here. So if I wanted to quickly sketch this, I would see that I have, let's actually center this. I have a y, I have an x. I have intercepts at 3, negative 1, x-intercepts I should say. And I have a y-intercept at 12, I think it was. Yep. A y-intercept at 12. And I have a turning point at, maximum turning point at 1 and 16. So that's about up here. So my turning point 1, 16. And if I wanted to sketch this out, I would get something that looks like this. Passing through my y-intercept and coming back down through my other x-intercept here. Obviously I've drawn this in a slightly dodgy way, but this is how we can work with our factorized completed the square form and find all of the key bits of information. So the turning point, whether it's concave up or down, how far it's shifted, how far the turning point's shifted to the right or left or up and down as well. So in the x and y directions. Now, in this particular example, we were just given the factorized form right off the bat. Now for the next two, I want to actually use what I know from completing the square in order to find these. So I want to sketch all of these graphs, and we are going to start with this one. Y equals to x squared plus 6x plus 15. And I want to factorize this using completing the square. Now, when we complete the square, remember we have to look at this particular term here. And we want to divide that by 2 and square it in order to add. That's going to give us a perfect square on one side and the constants on the other side. So if I do that, I take my b on 2, which is going to give me 6 on 2. Because remember, just this coefficient in front of x we call b, this one we call a, this one we call c. Okay, so when I do this using completing the square, I'm going to get y equals to x squared plus 6x plus 6 on 2 squared. And Remember, I can't just add this out of nowhere. I have to subtract it again in order to get something that is the same as this guy up here. So what I add for my completing the square, I need to also take away, and I have plus 15 at the end here. Okay, so this is going to give me y equals to x squared plus 6x plus 9, because 6 over 2 is 3. Squaring that gives me 9 minus 3 minus 9 plus 15. Okay, and just simplifying that, I get here, if we notice, I have my perfect square. Once again, this is going to factorize to give me a perfect square. And over here are my constants. Now you can hopefully already see how we are building towards my actual form that we defined up way up here. We're going to see how that works once we factorize this. So doing this, I'm going to just go through it quickly because this video is assuming we all know how to complete a square. So I'm going to write this in its factorized form. This is a perfect square looking like this. And minus 9 plus 15, that gives me positive 6. So now we have all the important elements again. We have my vertical translation. We have my horizontal translation. And we have, remember when there's nothing here in front, we can just think of that as a 1. So this gives me my vertical dilation and whether it's being reflected or not. So this is just a regular parabola. There's no actual dilation happening because it's just a factor of 1. And this is positive, so that means it is a concave up parabola. Okay, now let's have a look at what's being translated, because that's going to tell us where the turning point's going to move. So instead of having a regular parabola like this, my easy y equals x squared parabola, we want to consider these particular transformations. Now firstly, I have a positive 3 here. So that means that this horizontal translation is going to move it 3 units in the negative x direction. So I'm going to get something like this. This is my transformation moving the turning point 3 units left. And once again, I need to consider my vertical translation. So this is going 6 units up. Now let's put it here. Now I want to go 6 units up. So that's going to look something like this when I end up transforming it fully. So if we look, my turning point has gone from 0, 0. It's gone 3 units to the left, which gives me minus 3 in the x, and then still 0 in the y. And it's gone 6 units up, which gives me minus 3 in the x and 6 in the y. So that means my new turning point is at negative 3 and 6 for my particular equation of my parabola. And our completing the square tells us this in a really nice way. And once again, this is a concave up parabola, so this is going to be a minimum turning point. So we can say for part A, we have a minimum turning point at negative 3, 6. Okay, let's find the other key ideas. So let's find for part B the y-intercept, and we get that when x equals to 0. So subbing in x equals 0, that's going to give me y equals 0 plus 3 all squared plus 6. And that gives me 3 squared is 9 plus 6, which gives me 15. So this is my y-intercept. And my x-intercept is going to be... that's going to be, when y equals 0. Okay. So, when I substitute this in, we're going to look at something really interesting that ends up happening. Now, I'm going to have, subbing this in, 0 equals to x plus 3 all squared plus 6. Now, when we go to solve this, right, I'm going to try to do this the same way I did before. I'm going to subtract 6 from both sides, and that's going to give me minus 6 equals to x plus 3 all squared. And I'm going to try to do the same thing I did before. I'm going to try to square root both sides. So, what I'm going to get here, on the left I'm going to get the square root of negative 6, and on the right I'm going to get x plus 3. But with this guy here, we learned this when we talked about the discriminant. Can we have a negative number inside a square root? A real, and to give me a real answer. So if you pop this into your calculators, you will see something come up that says math error. Because with real numbers, we can't take the square root of a negative. That will not give me a real solution. So we can say here that our parabola, because we can't find a real solution here, there are no real solutions. But what does that mean? So no real solutions just means, in the context of this, no x-intercepts. And if we look up at the rough thing I sketched before, it never actually crosses the x-axis. Look at this guy here. Because it's been shifted up, the lowest it goes is this turning point, negative 3, 6. It never actually passes through the x-axis. So that's why it's going to make sense that we can't actually solve the equation for the x-intercept, letting y equal to 0. So that means there are no x-intercepts. So no real solutions, or in other words, no x-intercepts. Okay, so if we draw this now, let's look at all the key bits I found. I have y, I have x. Now I have a minimum turning point at negative 3, 6, and I have a y-intercept of 15. And if I draw this out, I'm going to get something that looks like this. And these are the only pieces of information that I can use. Because we had no solutions, no x-intercepts, I can still draw this with my turning point, considering whether this is concave up or down, as well as a y-intercept. Alrighty. Let's try one last example to really get the hang of this thing here. For example 3, we are looking at the equation of a parabola y equals x squared minus 3x minus 1. And we want to solve this using completing the square. So we're going to naturally get this into the completing the square form. So that means this number here, negative 3, we have to take half of that. We have to take b on 2. So that's going to give me negative 3 on 2. And in order to make this a perfect square, we have to add that on and square it. That's going to be our constant at the end of the perfect square. So our equation here is going to be y equals x squared minus 3x plus minus 3 on 2 squared. And remember, we can't just add this out of nowhere. We need to subtract this again to give me negative, oh, sorry, we have minusing 3 on 2 here. And then we just want to have the negative 1 at the end. Okay, so now that we have it in this form, we can condense this bit into a perfect square. We can factorize this really nicely to give us a perfect square. Now, if we remember from how we did that in the previous videos, the perfect square just ends up being x as well as my number here, 3 on 2, and the sign is going to be the sign we have here. So that gives me x minus 3 on 2 squared, and then this thing here, minus 3 on 2 all squared minus 1, just gives me minus 13 on 4. So now we have this in the same form as before. And this tells me right off the bat, now that we're used to this, we can just read off what the turning point is going to be. First of all, this number in front of my x minus 3 on 2 all squared is 1. So that means I have a concave up parabola, meaning I have a minimum turning point. So I have a minimum turning point at, and here, these values here, how much it gets horizontally translated or vertically translated, that tells me where the vertex moves. So I have a negative here. So remember, for the x values, we go in the opposite direction. So my x coordinate is going to be 3 on 2, and my y coordinate is going to be negative 13 on 4. So this is my minimum turning point at these coordinates here. Now for part B, we want to find the y-intercept. We get that when x equals to 0. So we have 0 equals to, y equals to 0 minus 3 on 2 all squared minus 13 on 4 and we can just substitute this into either one here, but we can do this, if your y-intercept, if you find it easier, you can substitute it straight into here. Some of you may find that a little easier, or we can substitute it into this form, but we're going to get the same answer regardless. So negative 3 on 2 all squared is going to give me 9 over 4 minus 13 over 4. And that's going to give me minus 4 on 4, which just equals to minus 1. So my y-intercept is going to be minus 1 down here. And finally, I want to find my x-intercept. And I get that when y equals to 0. Now, substituting in the y equals to 0, and I'm going to get x minus 3 on 2 squared minus 13 on 4. Now I'm going to factorize this one in the different way we looked at in the previous series when we looked at completing the square. Instead of just moving this 13 on 4 to the other side and solving it that way, I mean, that's definitely a way we can do this. Now I'm just going to do the other way so we can practice. Now in the previous series we said that when we had this term 13 on 4, we can write that as any term as minus and the square root of this thing here, all squared. Because the squaring of this is going to cancel out the square root to just give me this guy here. And what we can do now is we can notice that there is a difference of 2 squares here. And we know how to factorize these. Okay, so we're going to get 0 equals, now we're going to get here, in my first bracket, x minus 3 on 2, and we are going to get the sign of positive, and we have root 13 over, and the square root of 4 is going to be 2 here, and my other bracket is going to be the same thing, except this sign is going to be a negative. That's how we work with our difference of 2 squares factorization. So we get x minus 3 on 2 minus root 13 on 2. Okay, so now we want to use our null factor law. We notice that each of these, in order to get a solution of 0, one of these has to equal to 0. That's the only way we can get that as a solution, because we have a product here. These are multiplying. So in order to get 0 as an answer, one of the numbers multiplying by one another has to be 0. So we get 2 cases here. We get the possibility for x minus 3 on 2 plus root 13 on 2 to equal to 0. Or we can get x minus 3 on 2 minus root 13 on 2 equaling to 0. And then we just want to solve these. So for this one, we can just add 3 on 2 to both sides and subtract root 13 on 2. And the same thing here, except we want to add root 13 on 2 to get x on its own in both of these cases. So my solution is going to be x equals to 3 minus root 13 all over 2, because they have the same denominator here. And we are also going to get a solution of 3 plus root 13 over 2. So those are my 2 x-intercepts here. And finally, I can draw this. It's going to look a little messy because now I'm working with surds with my x solutions, but you can just put these in your calculator and round them off. But I'll just draw what this roughly looks like. We have y, we have x. Okay, we have a y-intercept of -1. We have a minimum turning point of 3 on 2, -13 on 4. And then we have our 2 x-intercepts. So one here is going to be 3 minus root 13 over 2. And here we have 3 plus root 13 over 2. And we're just going to sketch this off now. And we get something looking like this. I know my drawing's a bit dodgy, but all the key ideas are here. And now remember, when we work through these types of questions, we are just sketching parabolas. We're just giving a rough guideline, a rough picture of what this would look like. And what this involves, to recap, completing the square tells me a new form which I can just read off to see what translations are being done to my turning point and see where this turning point moves. So that's actually really useful because the turning point is one of those key pieces of information. And then we can just find the y-intercept from substituting x equals 0 into the equation, and finding the x-intercepts we get from solving these quadratic equations via completing the square, which we've done a lot of. Now you can either use this difference of two squares method, or you can just go ahead and just solve the equation by getting everything to one side and having x on its own. Sort of like what we did for up here. And this is how we can start to think about sketching parabolas via completing the square. If you've stuck with me all the way through, thank you so much, but I'll see you in the next video where we'll talk about sketching these parabolas using the quadratic formula and the discriminant, which some of you may find a little bit easier. But I will see you there.